Hi everyone. Today we'll be talking about the pipeline for state-of-the-art NLP. My name is Anthony. I'm an engineer at huggingface, the main maintainer of tokenizers, and with my colleague Lysander, which is also an engineer and maintainer of huggingface transformers. Uh, we'll be talking about the pipeline in NLP and how you can use tools from Hugging Face to help you with that. Your feedback is important to us. Don't forget to rate and review the sessions. So before we start, I'd like to quickly introduce Hugging Face for those of you that never heard about us. Everything started when we were trying to build your best friend, the conversational AI, an AI capable of listening to you and talking with you about any subject. If you've seen the movie Her, you know what I'm talking about. Let's say it's quite an ambitious goal, and we had a lot of fun while trying to achieve it. We started to open source the tools we built along the way, and we've been very surprised by the way it's been received by the community. Soon enough, we were spending all our time on these tools, making them better day after day, and here we are today. Transformers is our most successful project and is the most popular open source library for NLP today. We have close to 30,000 stars in GitHub, more than 1,000 research papers mentioning it, and many companies are using it in production every day. We are now pursuing a new goal, which is to help improve the NLP and make it accessible to everybody. And we recently raised a new round of funding to pursue this goal. We now have multiple open source projects that can help you work at many different steps of the NLP pipeline. And we are going to show you two of them. So today's menu, we'll talk about transfer learning in NLP and how it applies to transformer networks. Then we'll dive into the tokenization, followed by the transformers models. And now let's get started with my colleague Lysander. We'll start with the transfer learning.
All right, thank you, Anthony. So we'll take a look at transfer learning, especially transfer learning in NLP, and especially applied to transformer networks. So in a few words, NLP took a gigantic turn in 2018 with the arrival of the transformer architecture. So it arrived in 2018 with the Vaswani transformer, and immediately after the GPT and BERT transformers arrived and obtained state-of-the-art results on many different NLP tasks. First of all, before we dive in how transformers work and how transfer learning makes them so efficient, let's take a quick pause to understand what is exactly transfer learning and how it's different to traditional machine learning. So traditional machine learning, you would have multiple tasks and you would have multiple learning systems which would all need to learn on that specific task. So if you had 3 different tasks, you would need 3 different learning systems. And there was no really multitask systems, or not really, you weren't focusing your efforts on different tasks at once. And this works all right. However, some tasks can actually leverage some shared knowledge across different tasks. For example, if you're working with text, like 2 different tasks that concern text, well, the underlying principle is language. So if you have one task that understands language, then another task can surely use that knowledge that was acquired and use it for its specific task. which is exactly what transfer learning tries to do. So you have one or multiple source tasks on which you train your learning system. And then that's not really your target task, but your target task can use the knowledge you acquired using those two tasks, using the training on those two tasks so that it gets better results with less data, for example. And so how does that apply to NLP? Well, with sequential transfer learning, which is very similar to what I explained. So it's done in two steps. The first step is the pre-training, and the second step is the adaptation, or also called fine-tuning. The pre-training is a very computationally intensive step where you have a lot of data, you require a lot of compute, and you're basically trying to cram as much knowledge as possible in different systems. And those systems can range from word embeddings like word2vec or GloVe, or very recent transformer networks like GPT, BERT, or distill BERT. And once you have this general purpose model, you're going to try and adapt it to different tasks. And in order to do so, you require less data since you already have a strong knowledge base. Right, so now how does this apply to transformer networks? So transformer networks, in a few words, are very, very large neural networks. They range from a few million parameters to billions of parameters. The biggest, the transformer network that has the most amount of parameters is GPT-3, which was released last week, and which has 175 billion trainable parameters. And so with such a big amount of parameters, you actually have a very big capacity, and you can train those very big neural networks on very big data sets. However, one flaw of this is that it requires a lot of compute to be trained. And so that's where transfer learning really kicks in. That's where it's really interesting. Because starting from a base model, in order to obtain a general purpose language model, so a language model that's specific to a domain, let's say text or language, but completely task agnostic, well, you would need thousands in computes, a very, very large corpus, and days or even weeks of training just to get to that stage. However, once you have the pre-trained language model, then fine-tuning it to different tasks is actually very easy. You only need small data sets because most of the knowledge is already in the model. So you don't need your base model to get an understanding of language just from this small data set. You're completely relying on the previous training and just fine-tuning a bit on it for that specific tasks. So transfer learning is really useful in the case of very large models like transformer networks. And that's where model sharing is especially important, because reproducing a pre-training is completely impractical. It costs a lot, and since it's general purpose, it's completely task agnostic. So it's very important to share that pre-trained model so that other users may just use it and fine-tune it on their downstream tasks or on their own data sets. And this is something we're very proud of at Hugging Face, where we allow the easy retrieval and distribution of models entirely for free so that users may share compute. Right, so now let's take a deeper look at the inner mechanisms of transfer learning, of the pipeline for natural language processing, pre-training and fine-tuning of transformer architectures. So the transfer learning pipeline in NLP is composed of two big steps. The first part is the tokenization aspect, which Anthony will present you in a bit. And the second part is all the prediction aspect. So the tokenizer's goal is to get some input, like a sequence or a sentence, a dump of text, and convert it into inputs understandable by the model. Once these sequences have been converted to understandable inputs, then these can be fed to the model, which can then do a prediction on top of it. So how does pre-training a language model works? There's different ways of doing it, but the most frequent and the best way to do it is via language modeling. So learning to predict a text given other texts. One huge advantage of this method is that it doesn't require human annotation. And since pre-training requires a lot of data, not requiring human annotation is a very big deal, because you don't want to have to annotate a lot, millions of examples, when you can just leverage the, well, in this case, self-supervised aspects of language modeling. That's also very interesting in the case of languages that have that only have a few data, low resources language, low resource languages, because these languages in these languages it's very hard to acquire data sets that have sufficiently annotated data to perform a pre-training. However, just obtaining a dump of text is easy enough and can be used to obtain a sufficiently good pre-trained model. So let's take a quick look at how language modeling operates in NLP. With one, we'll look at two objectives right now. The first one being masked language modeling, or MLM, which is also known as the closed task, and is a very old language modeling method. And what we're trying to do here is mask some of the inputs and ask the model to predict what was instead of the mask. We're going to ask it to fill the mask. So in a traditional pipeline, in traditional NLP pipeline, this would look like the following. So you have a sentence, the pipeline for state-of-the-art natural language processing that you first tokenize. So you convert it into tokens, and then you mask one of those tokens. So for example, here the token natural was masked. It was replaced by a masked token. And you then ask the model to replace that masked token. So for example, here we ask the model to replace it and give its 5 most probable answers, which are natural, artificial, machine, processing, and speech, which all make sense in that context. So that's already pre-trained model that did this completion. But at first, of course, the model wouldn't do such correct predictions. And by making a loss out of it and training it, that's how you would obtain a pre-trained language model. The second objective is the CLM language model, CLM objective, sorry, where here, instead of masking some of the inputs, you want the model to predict what's the next token, what's the token following the sequence. And so this is interesting because it actually trains the model to do text generation. Since it's trying to always generate the next token, you can chain that, and it will, at the end, generate a sequence that has been, it will generate a sequence just from the context that you gave it at first. And so this is interesting, but it only attends to the left-hand side context compared to the MLM objective that we saw previously, which since you're masking a token that can be in the middle of the sentence, you can have access to both right context and left context. Whereas here you only have access to left context. So usually CLM has doesn't get as good results on downstream tasks as the MLM pre-training does. However, it allows for text generation, which is a very useful feature. All right, so now I'll let Anthony present the tokenization, which is one major aspect of the natural language processing pipeline.
Yeah, let's dive a little bit more on the tokenization now. So I want to start by quickly talking about the role of the tokenization. So as we saw in NLP, our inputs, the data that we generally processes basically some raw text. Like in this example, Jim Henson was a puppeteer, but our models obviously only work with numbers. So we need to find a meaningful way to transform this raw text, these strings to numbers. That's what the tokenizers do, and there are a lot of different ways to do this, but our goal is generally to find the most meaningful representation, the one that makes the most sense for our models, and possibly the smallest one too. So let's see some examples of tokenization algorithm and questions we get to ask ourselves with this. The first kind of tokenization that comes to mind is simply based on words. Um, it's really easy to set up and use with generally just a few rules, and it yields good results. In this case, we want to separate the raw text into words and find a numerical representation for each of them. This usually requires splitting the text somehow, and we have to choose how to do it. Do we want to keep the punctuation with the words, or maybe separated in their own tokens, or even not at all? With this kind of tokenizer, we generally end up with some pretty large vocabularies, words like dog, different words like dogs, and they end up with a different representation. The same applies for run versus running, for example. And all of these different words get an associated ID, generally starting from 0 and going up to the size of the vocabulary that we'll use to identify each word. So the more words we have, the more IDs we need, obviously, and the bigger the vocabularies. This also means that we generally need some token to represent any word that is not in our vocabulary. This is what we call an out of vocabulary token, also known as UNC or unknown token. Now, we don't like this token because it means we are not able to represent some of the words we might see, we might get as input, and we are losing information on the way. So that's something we want to avoid as much as possible. And so one way to reduce the risk of having out of vocabulary tokens is to go one level deeper. I'm talking about character-based tokenizers. In this case, we now split our text in characters. And one of the advantages is that we end up with smaller vocabularies. Also, we have a lot less out of vocabulary tokens since the words can be built from these characters. But yeah, we get to ask ourselves also, do we want to keep the spaces and the punctuation or not? One thing about this is that intuitively we think that kind of lack in terms of information since each character doesn't mean a lot separately. This is not true for some languages like Chinese, for example, where each character carries more information than in Latin languages, but in English, for example, each character doesn't mean a lot by itself. And another thing to consider is that by using such techniques, we end up with large amounts of tokens to be processed by our models. And this can have an impact on the size of the context we can carry around, for example. Now, we've seen some good results with this kind of tokenizers, so it really is interesting to consider in some cases. And we can also think about another technique, which is built from the previous one we saw about words, and then having as a fallback the character-based tokenization when a word is not in the vocabulary. But actually, let's see something that is even better than that. And I'm talking about third-word tokenization. You might have heard about BPE or byte pair encoding before. This algorithm was initially used for compression, as introduced in 1994 by Philip Gage, before it got applied to NLP in 2016 by Rico Senrich and his co-authors in the paper neural machine translation of rare words with subword units. And this algorithm brought some really interesting improvements. The idea with BPE is to start building an alphabet composed of Unicode characters that will serve as the base vocabulary. Then we start building new tokens for for the most frequent pairs we find in the original corpus. So, for example, in English, the letter T and H are often seen together, so they end up being merged in a new token TH. And later on, we might see that TH is actually often seen next to the letter E, so we merge it to build the token Z. And then we keep building up more and more tokens up to some target vocabulary size. Since we start from the characters and build up to words, generally when a word is not part of the vocabulary, we are able to use multiple tokens to represent it. In this example, you see that tokenization can be represented by token and ization. The same would apply for standardization, for example, which could be split in standard and ization. And so these subwords end up having a lot of semantic meaning, and they are also space efficient. We can have very good coverage with relatively small vocabularies and also less known tokens. There are obviously other techniques out there, like the byte level BPE, which is very interesting. It was introduced with GPT-2 by OpenAI and used bytes as base alphabets instead of Unicode characters. This means that the initial vocabulary fits in 256 different characters, which is the number of values byte can have. And yeah, instead of the 100,000, more than 100,000 different Unicode characters. And so there is also WordPiece, which is a form of subword tokenization tool, actually very similar to the way BPE works, used by Google in models like BERT, or also the more recent Unigram, originally implemented in Centenpiece, which brings some improvements over BPE by improving the way we merge tokens. So now, knowing all of this, I can now tell you why we decided to build a tokenizers library and how it works. So the first reason is simply for performance. Our models usually run with frameworks like PyTorch, TensorFlow, or even Onyx, and all of these provide great performance today. But the tokenization is often happening in pure Python, and it ends up being really slow, even sometimes a bottleneck in the NLP pipeline. So having to pre-process your entire data set before actually training your model shouldn't be a requirement, because this means that whenever you want to change something, you'd have to start over, and obviously it can become really cumbersome. So we definitely wanted to improve this experience and provide a real-time tokenization that you wouldn't even notice. It is also a great occasion to have all the various tokenization algorithms under one roof with a shared API. This makes experimenting way easier in switching tokenizers a breeze. We want it to be easy to share your work and access the work of others. And finally, we also want to make it really easy to train a new tokenizer, for example, on a new language or a new data set or whatever. So now let's see how we actually do this. Tokenizer is actually a pipeline. The input text goes through this pipeline, and in the end, you get something ready to be fed to your model. So the first step is the normalization. That is where we transform our input. Generally, that is where we're going to strip white spaces, for example, or lowercase everything for language that, um, um, yeah, okay, sorry. Uh, can we start over the first one? Okay. The first step is the normalization. That is where we transform our input. Generally, that is where we're going to strip white spaces, for example, or lowercase everything, maybe apply some Unicode normalization. Then we have the pre-tokenization. In this step, we take care of pre-segmenting the input as needed. In most cases, it means simply splitting on white spaces, for example, for languages that use white spaces, but really it could be anything that makes sense for a specific use case. Once all of this is done, we're ready to apply the actual tokenization algorithm. This is where BPE, Unigram, word level, or any other tokenization algorithm does its magic. And finally, the last step is the post-processing. Here we add the special tokens, like for example, the CLS and SEP in BERT. We take care of truncating the input so that it fits the model. We pad if necessary, etc. So now let's see some code and how to build custom tokenizers. This first example shows how to build a byte level BPE. As you can see, we start by building a tokenizer based on an empty BPE model. We attach a normalizer. In this case, this is a classic Unicode NFKC normalization. We also attach our pre-tokenizer. Here, this is a byte level, which will take care of splitting the raw text to words, if possible, and transform the input into the right representation so that we can process the text as byte level. This also means that we need a decoder now. This one will take care of transforming the tokens back to readable Unicode characters when we want to decode from IDs back to text. And that's it. Our tokenizer is ready and we can now train it. For the training, we specify the target vocabulary size as well as the special tokens we plan on using. We give it a bunch of files and just let it work. The training step actually trains the model. So here, when the training is done, it just means that our BPE model is not empty anymore. It now has a vocabulary. And I want also to show you another example of tokenizer. In this case, it's a word piece like the one used in BERT. So just like before, we initialize the tokenizer, this time with an empty word piece. This time we use the sequence as the main normalizer, which is just a utility helper that we can use to combine multiple normalizers. In this case, we want to strip each string we receive as input and also lowercase everything. We use a simple white space pre-tokenizer that will split on white spaces and keep the punctuation as separate tokens. And we set up our decoder. In this case, we needed to decode the IDs while treating the double hashtag symbol, which is specific to WordPiece. And once again, we're ready to train. There is a final step here though, which is about setting up the post processor. If you remember from before when we described the pipeline, this is the part that actually adds the special tokens. And now we're actually defining this here after the training because we need to initialize it with token and a token ID for both the SEP and CLS tokens. And in order to be able to use the token to ID method on the tokenizers, we can do this only after it's been trained. So now, after these examples, our tokenizers are ready to be used. We can also specify maximal lengths if we want by enabling truncation. This would ensure that the inputs to our model will always be of the right size. We can also enable the padding, for example, so that all the sequences we encode as batches of the same length. In this case, we specify that what are the pad token and pad ID that we want to use. And we can save these tokenizers. Everything we define before that will get will get saved in this file. The normalizer, the pre-tokenizer, the padding options, everything. This means that whenever we want to use this tokenizer in the future, all we need is a single line of code. We initialize it from the file and we are ready to use it. If you want to try another tokenizer, your code does not change, you just change the file from which you load the tokenizer. Now, of course, each tokenizer can be used to encode some input text, and here we actually support multiple types of inputs. We can encode single sequences, but also pairs of sequences. For example, if you want to do question answering, you would encode the context and the question as a pair of sequence. You can also encode batches of sequences, both single and pair of sequences, and even mix these if that's relevant. And we even support pre-tokenized inputs. For example, if you want to do some entity extraction and that your data set is already pre-tokenized. And in all of these cases, when you encode, you get an encoding back. This encoding contains all the things that you may need, like the IDs, obviously, but also the generated tokens if you want to check what it looks like. This example shows you what some byte level tokenization would look like with its strange characters in front of each token. This character actually represents a white space in byte level. And we also provide the offsets for each token so that you can extract text from your original input if needed. That's something really helpful in the case of question answering, for example, where you want to extract the answer from the original text and maybe highlight it. You can also find special tokens mask and attention mask if you need them, and a lot of other things also that I'll let you discover. So yeah, try it. It's as easy as using pip install tokenizers or npm install tokenizers in Node, and we'll keep on adding bindings for new languages in the future. Now, I let Lysander talk to you about transformers.
All right, thank you, Anthony. So transformers is another big part of the natural language processing pipeline because it takes care of the prediction right after the tokenization. So since 2018 and the arrival of the first transformer architecture, there really has been an explosion of the number of transformers that have arrived. Just to name a few, GPT-3 was released last week, and before that there was Mina from Google and several others the past few months. And each of those transformer architecture is different, is a bit different to the previous one. For example, BERT uses word piece tokenization, was trained with masked language modeling and next sentence prediction, while GPT-2 uses byte level BPE tokenization and was trained with causal language modeling. And it's the case for every single transformer model. So even though they're very similar, they have some inner quirks and some slightly different APIs. What we try to do in transformers is offer all of those transformer architectures to be very simply usable under the exact same API. While doing so, we try to make it accessible to as most users as possible, given that we first started with only supplying our models in PyTorch. Now they're all available in both PyTorch and TensorFlow since last September. And since last month, we have our first two models, BERT and Roberta, in the JAX framework from Google. All of those models train and run on CPU, GPU, and TPU with each framework specific optimizations. So XLA for TensorFlow, TorchScript for PyTorch, and others like half precision and others. So to understand how an inference script would look like using transformers, it leverages the two abstract classes, which are pre-trained tokenizer, which is completely based off of Hugging Face tokenizers that Anthony just presented you, and pre-trained model, which is an abstract class encompassing the models. Both pre-trained tokenizer and pre-trained model offer the exact same API, whichever model you use, whichever model tokenizer pair you choose to use. So for example, if you would want to use BERT and write a script with it, an inference script with it, it would be as simple as just changing BERT to GPT-2 to just completely change the transformer using it. So with transformers, what we try to do is to, well, we publicly host pre-trained tokenizer vocabularies and model weights on a model hub, which allows easy sharing and easy use of pre-trained models and tokenizers. So right now we have more than 1,600 model tokenizer pairs that you can use very simply, as shown in the code sample here, using just tokenizer from pre-trained and model from pre-trained as well. Another abstraction that is available in transformers is the pipeline abstraction, which handles both the tokenization and prediction. It uses reasonable defaults, which means that you can get state-of-the-art results, state-of-the-art predictions without tuning any settings. However, they're still very customizable, which means that if, for example, you want to use a pipeline in a different language than English, you can totally just input which pre-trained model and tokenizer pair you would like to use, and it will automatically download it from the model hub and use that pair that you mentioned. So let's check a few use cases. That's where it gets really interesting. So here we have sentiment analysis, which is a kind of sequence classification. We'll be for the next three examples, we'll be using the pipeline abstraction, and for the last example, we'll be looking at how it looks without using the pipeline abstraction. So just using the bare bones tokenizer and model to see what really happens inside the pipeline. But here, for example, with the pipeline, it's very easy to do sentiment classification. You would start by first importing the pipeline and then initializing it with the task that that you want to complete. So here's sentiment analysis. Then you would just call this object NLP with the sequence that you want to classify according to a sentiment, positive or negative. So the result of NLP, I hate you, results in the negative label with a score of 99.9%. And the result of NLP, I love you, results in a positive label with a score of 99.9%. Now for next task, the question answering, which I find absolutely incredible, the question answering task in natural language processing is given a context, given a context and a question, it extracts an answer from the context to give an answer to the question. So here you would do, like the previous slide, you would initialize the pipeline with the task, question answering, and then define a context, which in this case is, I will read it out loud. So extractive question answering is the task of extracting an answer from a text given a question. An example of a question answering data set is the squad data set, which is entirely based on that task. If you would like to fine-tune a model on a squad task, you may leverage the run squad.py script. So then you would call the NLP variable with a question and the context that I just read. So for example, NLP, what is extractive question answering given the context? And it returns a result with the score, the start and end location of the answer, and the answer. In this case, the task of extracting an answer from a text given a question, which is entirely correct. And for the second question, what is a good example of a question answering data set? The answer squad data set, which is correct as well. So for a causal language modeling or a text generation, which is the same thing as we've seen previously, you would first initialize the pipeline as we've done previously with the text generation string, and then create a sequence that you would like to be completed. So for example, here the Spark plus AI summit, we want the model to complete the sentence following that initial context. And so we do NLP sequence, which results in the following generated text. The Spark plus AI Summit was a special event held in January 2016 to celebrate the emergence of a major and enduring innovation, the Spark Plus. The event opened with a keynote by Dr. Stephen Hawking, creator of AI, although it still has many of, etc. So you can see here that the text is syntactically coherent, even though it's factually incorrect. All right, now as an example using the tokenizer and models without relying on the pipeline abstraction. So here, we're going to do sequence classification again, similar to the sentiment analysis, but we're going to do a different task here. We're going, as you can see in the code sample, we're loading the tokenizer and model checkpoints, BERT base cased fine-tuned MRPC. BERT base cased means that it's the original BERT base with the case vocabulary that was released by Google when it released BERT. And fine-tuned MRPC means that we've fine-tuned this checkpoint to the MRPC task. MRPC is the Microsoft Research Paraphrase Corpus, which is a data set that tries to identify when two sequences or two sentences are paraphrases of each other. So here we initialize the tokenizer and model from that checkpoint. Next, we define the classes, so not paraphrase and is paraphrase, and we define three sequences. The first one is the company Hugging Face is based in New York City. The second one is apples are especially bad for your health, and the last one is Hugging Face's headquarters are situated in Manhattan. The first and second sequences are completely unrelated, so definitely not paraphrases of each other. However, the first and last sequences are practically mean the same thing. So maybe they're not actually paraphrases, but they're very, very similar to each other. So we would want our model to predict that the first and last sequences are paraphrases. So we define that we now use the tokenizer to encode the sequence pairs so that it basically combines the two sequences into a pair using the model's special tokens, and builds tensors that can then be used by the model to output the prediction. That's why we have return tensors equals PT, which means that we want tensors to be returned. So paraphrase and not paraphrase here are two dictionaries containing PyTorch tensors that the model will use to really do a correct prediction. So now we spread the paraphrase and not paraphrase dictionaries in the model and get the first result, the first return of the model. Since the model returned tuple outputs, which contain a lot of different data on how the prediction was computed, we only want the first result, which is only the classification logits. So the paraphrase classification logits and the not paraphrase classification logits. Now we just pass these results through a softmax to make sure that our results are between 0 and 1, and we can do probabilities or a percentage of those, and we print the results. And we can see the results. Should the paraphrase is the first and last sequence, The result is not paraphrased 10% and is paraphrased 90%. So it did identify that the two sequences were very similar. And in the second case, should not be paraphrased. It's not a paraphrase at 94%, and it is a paraphrase at 6%. So here too, it identified which paraphrases. It identified that the first and second sequences were not paraphrases of each other. So using the model and tokenizers is still very easy and seamless, since we offer these high-level methods that allow converting inputs to that are converting sequences to model inputs very simply. But transformers isn't only limited to inference, it can also train models. And we do offer quite a lot of example scripts in our library in both TensorFlow and PyTorch for a few tasks that are listed here: named entity recognition, sequence classification, question answering, language modeling, both fine-tuning and from scratch if you want to do a pre-trained language model, multiple choice. And all of those train on both TPU, CPU, and GPU. As well as this, since our models are simply bare bones models in both PyTorch and TensorFlow, you can use it with the respective training frameworks. So for example, in PyTorch, you could just use it with a simple training loop or with PyTorch Lightning. And then TensorFlow, you could use it with Keras fit method or with the TensorFlow estimators. We also offer a trainer class that can be simply overridden in Python just to build a very simple training loop specific to NLP. So with transformers, with this presentation, we just grazed the surface of transformers, which offers many, many different possibilities. To just name a few that were added in the past few weeks, we've added the ELECTRA model and the ELECTRA pre-training method. We've added the reformer for very high efficiency, the long former for very, very large sequences, the encoder decoder architectures for translation and summarization. So now we've seen both the tokenization and prediction aspects of the full NLP pipeline, but is that really everything? Is that really everything that covers the NLP pipeline? Well, not really, because there's still the data part and the metrics part that needs to be covered. Since just obtaining data and feeding data to the tokenizer in a memory-friendly way and computing the metrics afterwards are two different tasks. Well, we've created the Hugging Face NLP library just for that, so that it offers in-memory mapping, and computing the metrics automatically. And the NLP library will be soon built on top of Spark, and currently offers more than 100 different data sets that can be used very, very simply by the tokenizers and transformers library. So that's it for the full pipeline of the current natural language processing using Hugging Face tools. Thank you very much for listening to our talk. Your feedback is very important to us, so please don't forget to rate and review the sessions. Thank you from both Anthony and I. Thank you very much.